Oakley dokley. This is the second part of the problem, which is calculating the magnitude and nature of the force in member J. This is member J just here. Now we know that you can use a method of joints, but the easiest method to use in this situation is a thing called method of sections. And that is where we are going to cut our truss just there where I've drawn that line. So I want you to imagine now we take all this section away and we now have a situation where I'll just draw it. You'd have this happening. You'd have your reaction at A, vertical and horizontal that we worked out. You could even draw in its actual resultant there. You would have a force going this way, a force going this way, and a force going this way. Now, you have to guess the nature of the force, and if you calculate and the sign is wrong, if you end up with a negative, in other words, you decide that if you said tension, it's actually compression, and if you said compression, it's tension, if you get a negative sign in your result. Now, a thing to remember is if you remove a member and you think about the forces that are being applied, if it collapses, it's going to be in compression, okay? So a good idea here would be to assume that we've got a tension situation there. You might want to say this one could be tension, that one's compression, and I'm going to say this one here also tension. And we now need to work out what's going to happen with this problem. And so this is going to be sum of moments once again, because any structure that is in equilibrium is, even if you take a section of it, that section is in equilibrium. If you take a single joint, that is also in equilibrium. So you can take a section of it, or you can take an individual joint, or you can take the whole structure. It's going to be in equilibrium. That's one of the wonderful things about this type of analysis, of static analysis of a structure. And it's one of the tools you can use to analyze this particular type of truss. In this wonderful subject that's called truss analysis. Practice will make perfect in this situation. So we're now going to say sum, we're going to get positive, and our sigma, which is sum of our moments about our point A, is equal to 0, because we like we said, sum of moments is going to be equal even to 0, even for a section. Okay, so we've sectioned through this line here. I'm going to call this line AA, just so you know that that's where we've cut the truss. And we're now going to work out our moments around this point A. Now, the wonderful thing about this is the RA vertical, which we've calculated, and the RA horizontal, all of these forces are acting through the pivot point. And if you're looking at moments, whenever the force is acting through the pivot point, it is not going to have an effect on the moments. The way of thinking about this is kind of like, if that's your door, and this is a hinge that opens and closes your door, if I'm trying to close the door by pulling on the door this way, it's not going to close, is it? If I'm going to try and close it by pushing this way, it's not going to close, because that force is acting through the hinge, okay? But if I act perpendicular to the hinge, the door will open and a moment will be created. So that's how that principle is in operation. So we need to turn around and say to ourselves, okay, does this one here, this force here, create a moment? No, it doesn't create a moment because it's acting through the pivot point. Does this force here create a moment? No, because it's pulling through the pivot point, okay? But this one here has a perpendicular distance from the pivot point, so it's going to create a moment. And also, this one here, okay, is going to create a moment. And assuming that this is in tension, in other words, pointing towards the joint, makes a lot of sense, because you know that your sum of moments has to be equal to 0. And the only force that is causing this to rotate in a positive direction is the 7 kilonewtons. So this one has to rotate the other way to cancel it out. Okay, so we're going to say sum of moments is equal to 0. So 0 and is equal to 7 times perpendicular distance, 1,000. Then we're going to say minus, we're going to say Fj. So this is force J operating this way, minus force J, which is what we're trying to find out, times we need a distance, okay? A perpendicular distance. Now we can break force J up into its verticals and its horizontals, and I will show you that method shortly. But for this type of problem, it might be an idea to invoke that wonderful idea of transmissibility of forces. So we can extend this line of force away. Okay, so we've gone out this way because we're looking for that distance from the pivot point that is going to be, and if you had your little triangle that gives you 90 degrees, it would be even better. But we're trying to work out that perpendicular distance from the pivot point. And as you can see there, that is the distance that we're looking for, this distance here. It's a triangle. That's a 90-degree point. So now we're going to be saying, well, okay, so how do we work out these angles? We've already worked out that this triangle here is 20, 20, and 140. We know that there's 180 degrees in a straight line, so we know that this angle in here is 40. And so we're trying to find out this distance here, and we know this distance here. Now we know that sine is opposite over hypotenuse. Do we know the hypotenuse distance? Yes, it's 3,300. Do we know the angle? Yes, it's 40. So we're trying to find this distance here. Let's call that distance J, because that's the one we're trying to work out for this moment. So we're going to say to ourselves, sine 40 is equal to dj, which is the distance we're trying to find, distance j, over the hypotenuse, which is 3,300. So dj is equal to 3,300 times sine 40. So dj is equal to try again, 3,300 times sine 40 is equal to 2121. I do it to 2 decimal places, 0.20. Okay, so we've got a distance. We're going to say 2121.20. Now we're going to say 0 equals 7,000 minus 2121.20 Fj. And we're going to say, we're going to make Fj the subject of the equation. Force J is equal to 7,000 divided by 2121.20 is equal to Fj is equal to 3.3 kilonewtons, and we've already said that it's pointing towards the joint, so that is in compression. So that is 3.3 kilonewtons compression. Did I get it right? Yes, I did. Genius. Okay, folks, I hope that all helps you. I will do one more video where we break down that force into its component vectors. But if you were to say to yourself, I'm going to work out this force J as its horizontal and its verticals, as long as you calculated those distances correctly, you would get the same result. See you in class.